All right, I want to talk in this segment about the Thomas algorithm. And what we're going to be doing is going through the segment on the Thomas algorithm from the Wang and Anderson 1995 text. All right, and so this PDF is loaded in Blackboard for you, and we can go through it. It's basically a form of Gaussian elimination, but it's just a little more efficient. All right, because we talked about how expensive Gaussian elimination is and how that scales as n cubed or n squared. And for purposes of our class, we'll say n squared. The Thomas algorithm scales as just a factor of n, all right? And it's much more efficient, all right? Now let's talk about why. At this point, I think you can translate between matrices and vectors and actual equations. So we have the equations written here, and we're used to having tridiagonal matrices for our one-dimensional solutions in this class, and that's what the Thomas algorithm is good for. Instead of running through every element of this whole matrix, including these corners that we know are empty, it only runs through the nodes that we, or the places where we know we have things, which are the diagonals and these two nearest off diagonals. All right, so what I want you to remember is that A, B, and C are the actual original coefficients in the matrix, and that F was our original set of knowns. Okay, and of course we're solving for the x vector. Okay, so, and this is written here, you can see, you can read the text, you can get through it, but I'll run you through it quickly. All right, so it's not that hard to turn this into an upper triangular matrix, right? You just need to get rid of these guys. So here we are turning this into an upper triangular matrix. To do that, these guys are going to convert from being C's to being betas. So these are new coefficients, and these stop being F's and become Y's because we've done our row processes on them. All right. So what we get here is, now we can unspring this. All right, so once we've done all this, here are the actual F's, all right? And here's that beta and the other coefficients. So that's what these rows really look like. And to save ourselves some writing, we're gonna define an alpha, which is gonna be these terms. And here, this is saying what it actually is for this real row, for ones and twos and threes, right? So let's look at this more generally. Oh, before we do it generally, all right, we can divide through, we can make this be alpha and then divide through by alpha, and the equation starts to look a little less crazy. It's not actually, it's the exact same equation, but we start to be able to isolate this diagonal, right? So now what we can do is, in terms of having our new system of equations here with betas and y's, this is the system we want to solve, this upper triangular system. And now we have equations that you can get from these guys, right? We have equations that say what alpha is and what beta is, right? So you can basically run down the rows, altering these guys. You know what they're going to be. They're not complicated equations, all right? And you can find out what y is immediately also, because we know what f was, we know how to get to y, we have an equation for alpha, right? And a was the original thing. All right. So the deal is that you can run through and solve for these things. Here's the actual solution. X equals y minus beta x sub I plus 1. All right, so when they start talking about recursive, right, you do need to review, go back up to the previous row. So that's what's going on. So the deal is you can solve this set of equations sort of all at once. You don't have to make it all diagonal and then solve for x. You can kind of do them all at the same time. We kind of know what the diagonals are pretty fast. We can, we kind of know what the off-diagonal coefficients and y are going to be immediately, right? And there's the previous row, right? It only depends on this previous row. Oh, we can kind of solve this all at once, just going down in one great big thing. It's not quite like that. You need to come down, and then you still do need to go back up, because here this is x at I plus 1. This one was y at I minus 1. So you still do need to get down and then come back up, but it's really fast. Okay? So, and what they've included here is an algorithm, and this is written in Fortran, but my experience is that if you can read MATLAB, Fortran isn't that tricky. It has some crazy things like their for loops are actually do loops, and the way they start them off is they tell you where the last line is going to be. It's going to be line 201. Oh, and there's line 201. So that's how this loop is defined. But this is it. This is the whole code. I mean, you see the end of page, right? So this is the whole code for doing what we just described. And it uses the same notation here that they described above. We have alpha, beta, and y. And here are our original coefficients. And x, that we want to solve for. And f, which was our knowns on the far side. All right, and I think you'll see how easily these translate. These are the equations from above. And here's that little bit of recursion. All right, and then at the end, hey, look at this. Here's begin backward substitution, and you just pdoonk. Here's our backward substitution in its do loop. So this is the forward part of the loop. This do, the 201 loop, and this do 203 loop is the back substitution, and it just pops the answer out much, much faster than if you went through all the other elements of the matrix. Now you can imagine that when we get into two-dimensional or any of the finite element ones, two dimensions. When we get into 2 dimensions, we need to go beyond just our tridiagonal matrices. And the deal is that they still come out as banded matrices. They don't fill the entire square matrix. They're going to be symmetrical, or at least the actual values in the off diagonals won't be exactly symmetrical, but you'll have stripes. The rows that are used are usually symmetrical, going around that diagonal. So you're still going to have a banded matrix. It won't be a banded tridiagonal matrix. It's going to be a banded, however narrow you can get your bandwidth, diagonal matrix, right? But you can imagine that's also why for us, our number of operations goes as n squared instead of n cubed, because we never have to deal with a full square matrix. We can always deal with a banded matrix. So that helps us get our number of operations down. All right, but the Thomas algorithm lets us get all the way down to scaling as n instead of scaling as n squared. All right, and that is enough of the Thomas algorithm.